Hello all. In this lecture video, we are going to discuss the concept of dynamic programming. So what is a dynamic programming? It's a general algorithm design technique for solving problems defined by recurrences with overlapping subproblems. So which solves the optimization problem which are overlapping in nature. So this concept is invented by American mathematician Richard Bellman in the year of 1950. Here the word programming meant not as a normal coding word. Here it means planning. How we are going to plan in order to solve that optimization problem. The basic idea behind in this dynamic programming is first you have to set up a one recurrence which indicates a solution to a larger instance to solutions of some smaller instances. Uh, you have to set up a recurrence equation which is going to give a solution of some smaller instances which indicates giving a solution to a larger instance. You have to solve the subproblems only once. Then record the solutions of the subproblems in a table. Finally, you have to extract the solution to the initial instance from that table. So normally in the divide and conquer, the problems, subproblems are solved by writing a recursive routine so that there may be chance of that problems may be solved more than once. So that kind of thing will be avoided in dynamic programming. The subproblems are solved only once. The results of the subproblems are recorded in a table. Later on, if you have to solve the same subproblem, instead of solving that subproblem once, we can look up the answer of the subproblem in a table. That is the main advantage of the dynamic programming. So we'll explain the concept of dynamic DP with small example or simple example Fibonacci series. So we know that the Fibonacci series is a one sequence which will start with 0, 1, 1, 2, 3 and so on. So that is, in order to obtain the nth term, you have to add the previous two terms in that sequence. So f of n is equal to f of n minus 1 plus f of n minus 2. You are initializing the first two Fibonacci numbers. F of 0 is equal to 0 and f of 1 is equal to 1. Okay. So this is in one way how we are going to obtain the nth Fibonacci number recursively by using the top-down approach. So this is what this recurrence f of n is equal to f of n minus 1 plus f of n minus 2. So here we note down this. Here this is f of n minus 3 is solved twice over here. See, here also we are solving once, here also we are solving once. Again, if you split this f of n minus 3, what will happen? F of n minus 2 and the another subproblem is f of n minus 1. So here also the f of n minus 2 is solved twice. Okay. But rather, if you are following the bottom-up approach, okay. So what we are going to do is we are using this f of 0 and f of 1. We are finding the next Fibonacci number f of 2 by adding these two numbers together. So 1 plus 0 is equal to 1. So in the next iteration, we are making that f of 2 becomes f of, in order to obtain f of 3, you have to add f of 2 becomes f of 1 and f of 1 will becomes f of 0. Okay. That is, you have to add these two previous numbers in order to obtain f of 3, f of 1 plus f of 2. So likewise, you can obtain what is f of n. So the same thing, but we are starting from this bottom-up approach. There in this top-down approach, we are finding this f of n. There you can find this more than one times that may be solved. The same subproblem. So instead of that, we can store the results of this subproblems in a table. Okay. So later on, this subproblem is solved only once. Later on, if you want to make use of this, what is the value of f of 1? Instead of computing that f of 1 or f of 3 once again, you can look at the value from this table. So that is the concept of the dynamic programming. So the other famous examples which can be solved under this DPS, computing a binomial coefficient, then change making problem, or coin change problem, then knapsack problem, traveling salesman problem, constructing an optimal binary search tree, Warshall algorithm for finding the transitive closure of a graph, Floyd's algorithm for computing all pairs shortest path. So first we'll discuss what is the knapsack problem. So what is that statement of the knapsack problem is, a given n items along with their weight of those items, that is W1, W2, W1, and the profit or the value of those items, and the knapsack capacity W. Okay, find the most valuable subset of the items that fit into the knapsack. So you know that this is an optimization problem. So the two of maximization, what we have to find us, you have to find the most valuable subset of the items that fit into the knapsack. So this is going to be your objective. Okay, most valuable items that fit into, you have to maximize the profit of the item inside the sack. So what is the constraint of the problem is, okay, that item fit into the stack. So whatever the item you are filling into the sack, the total capacity of the sack should not be exceeded. Okay. So we are going to solve this knapsack problem by using the concept of dynamic programming. So we know that in the dynamic programming, the first initial step is you have to set up a one recurrence, okay, which indicating the solution to the smaller instances of the problem. So if you solve all the smaller instances of the problem and store the results of the subproblem in a table, from that you can able to look into what is the solution to the main problem. Okay. So we are going to consider the instance defined by the first items and the capacity J. Okay. So there are only the two cases. Okay. You know that the capacity is the capital W, that is the total sack capacity. Whenever you are considering an item into the sack, there are only the two possibilities. Whether the item can fit into the sack, otherwise the item may not be fit into the sack. So if the item weight is less than or equal to this sack capacity, I mean the current capacity available, so that the item can be easily fit into the sack. So whatever the item if you are considering into the sack, that item weight is greater than the current available capacity. I'm not saying the total capacity. The current available capacity of the sack you cannot able to place. So there are only the two options, whether that particular item can be considered into the sack or it may not be considered into the sack. So first you have to solve the smaller sub instances of the problem and you have to record the results. Okay, for that we have to form a one recurrence which indicates a solution to that sub problem. So let V of ij be the optimal value of such instance. Then we can define V of ij is equal to maximum of either these two values, either V of I minus j, comma, sorry, V of I minus 1 comma j, or Vi plus V of I minus 1 comma j minus Wi if j minus Wi is greater than or equal to 0. So what we are considering, the j is nothing but the current capacity of the sack. So this is the current item weight. So if you subtract those two, which means that you are considering that item into that sack. Okay, so definitely that should be greater than or equal to 0. Then only it fit into the sack. Okay, so once if you are able to place the item into the sack, what is our objective? You have to maximize the profit. So you have to check into that when you are placing the item into the stack, whether which is going to increase the previous profit. Okay, then only you can able to place the item. So that's what you are comparing. So this is V of I minus 1 comma j is nothing but the value of the or the profit of the sack previously. Okay, suppose if you are considering that item into the sack, you have to add this previous item value along with this profit of that particular item. Okay, so if you add these two and find out whichever is maximum. Okay, maximum of vi minus 1 comma j comma vi plus vi minus 1 comma jw. Okay, so if j minus wi greater than or equal to 0. Okay, otherwise if the item cannot be fit into the sack, which means that the j minus wi is less than 0. That is, the weight of this particular item is greater than the current capacity of the sack. Okay, in that case what happened, which means that that item is not placed into the sack. So that what may be the previous profit of the sack, that is going to be the vi minus 1 comma j, that is the previous item, I minus 1. Okay, so this is what the required recurrence. Okay, so the first case is the item is considered into the sack. That case you have to find out when you are considering that item whether it is going to increase the profit of the sack. Okay, otherwise you have to retain that previous instance, previous item profit itself. The second case is the item may not be considered into the sack. That is, in that case we are not obeying the constraint of the problem at all. Okay. You obviously know that when you are setting a recurrence, you need some initial values also. So v of 0 comma j equal to 0 and v of I comma 0 equal to 0. I already say that the I is an items, j is the capacity, current capacity. Okay. So now we will discuss how to find the solution to this subproblems and how to record the solution in the form of table. So this is what the given instance. For example, the total capacity of the sack is equal to 5. They have given 4 items along with their value and along with the profit of that item or value of that item. So you are supposed to solve the problem using this dynamic programming concept. So I have already told you how to first set up a table which indicates the solution to that subproblem. So this is then I, that is ranging from this number of items. Okay, so this is the capacity will range from 0 to the total capacity of the sack. So what is the total capacity of the sack? 5. So the value will range from 0 to 5. Okay, so here the I value indicates the number of items. Again it will range from 0 to n. So 0, 1, 2, 3, 4 along with your indicating what is the weight of that item and what is the value of the first item, what they have given in the problem. So in the initial we know that v of 0 comma I equal to 0 and v of I comma 0 are equal to 0. Okay. So in order to fill the solution to that subproblem, there is a one tips available. So either you can calculate the value of the subproblems by directly applying the value in the recurrence equation. Okay. Otherwise, in order to compute the profit of that particular item, that is v of ij, that is in order to compute the value of the particular cell in that table. Okay, so what you have to consider is this, the maximum of the entry in the previous row. Okay, the maximum of the entry in the previous row, which means that for that current capacity v of I minus 1 comma j. That's what we have discussed. Otherwise, the another values and the same column and the sum of vi and the entry in the previous row and wi columns to the left. That is, we have seen in the recurrence now, which may be the maximum of vi minus 1 comma j or vi plus vi minus 1 comma j minus wi. So this is the v of I minus 1 comma j, that is the entry in the previous row, same column. Otherwise, you add the profit of that item, that is vi, and the entry in the previous row and wi columns to the left. So you have to subtract the weight of that item in the current capacity. You have to look up at that value. You add both these two, whichever is maximum, that is going to be the solution to that subproblem. Okay, so while solving that subinstance, you can easily come to know that what is this. So the table can be filled either row by row or column by column. Okay, so the initially the rows and columns are filled 0. No, first we will calculate for this. Okay, which means that the current capacity of the sack is 1. You are considering the first item into the sack, whether it can be fit into this. So what I told, if you are placing that item V of I comma j, so you are calculating 1 comma 1. So that is V of 1 comma 1. So what I told, you have to find out the maximum of the entry in the previous row, same column. So this is what you are going to calculate. Okay, so you go to the previous row, same column. What is the value will be available? 0. Comma, VI. Okay, what is the VI? VI means the profit of that item. 12 plus WI columns to its left. The same previous row, WI columns to left. What is the value of WI? That is weight of that item is 2. So from here there are no entries in the row, previous row. So there is no value at all. So that the what is the previous value of that item, that is going to be the solution to this subproblem also. V of 1 comma 1. Okay, so you can easily know that. So what is the weight of this item? 2. Okay, what is the current capacity available we are looking? So that is 1. So obviously you cannot able to place this item into that sack, since the current capacity what we are looking is 1. But what is the weight of this item? 2. Obviously you cannot place. So that what may be the previous item profit, that is going to be the solution to this sub problem also. That's why it is 0. Okay, so next we'll come to this. That is, we are supposed to find out what is the value of V of 1 comma 2. Okay, so that is maximum of, you go to the previous row, same column. What is the entry available over here? 0, comma. What is the value of this item? 12 plus, in the previous row, the entry which is WI columns to its left. So what is WI? That is 2. That is weight of that item. From here, you move on to the 2 column to its left. So 1, 2. What is the entry present over here? 0. So whichever is maximum, either 0 or 12. 12. So that's why the value for V of 1 comma 2 is 12. So easily you know that what is the current capacity we are looking now? 2. What is the weight of the item? So obviously that item can fit it to the sack. So previous item profit is 0. Now if you are considering that, that is going to be the maximum profits. That's why the value is 12. Okay. So next you have to calculate V of 1 comma 3. Okay. V of 1 comma 3. So again you go to the previous row, same column. The entry is 0 and you add the profit of this item and WI column to its left. Again it is 0. So 12. So for all these, the WI column to its left is because there are no more items you are considering previously. So that profit is 0. So when you are considering the first item after the capacity 2, so the profit is 12. So next, when you are considering this second item, okay, so this is obviously 0. You are calculating the entry V of 1 comma 3. V of, sorry, 2 comma 1. So that is item 2. The current capacity is 1. So easily you can look at this. The weight of this item is 1. The current capacity what we are looking is 1. Okay. So this row is finished. Okay, if you are considering the first item, what is that value we have filled? Next, you are considering the second item alone. So it means that it can be easily placed into that sack. Okay, for the current capacity 1. So obviously, what is that previous profit? 0. So 10. Okay, so that is the previous row, same column entry is 0. Okay, then you add 10 with WI column towards left. What is the weight of this item? 0. So 10 plus 0 is 10, whichever is maximum 10. That's why this entry is 10. The next you have to find out what is V of 2 comma 2. Look at. So V of 2 comma 2 is maximum of. So for this value, what is the entry in the previous row, same column? 12. Comma, what is the profit of this item? 10. 10 plus, what is the, you have to look at the entry in the same previous row, WI column towards left. So since the weight of this item 1, what is the entry in its one column towards left is 0. So whichever is maximum, 12. So that's why the value is 12. So because now what is the current capacity you are looking is 2. Okay. So for the current capacity 2, you have to check whether the item 1 can be placed or item 2. Both will not violating the constraint, because the weight of the first item is also 2. The weight of the second item is 1. So that any one item can be placed without violating the constraint. But what is our aim? We have to maximize the profit. If you compare the profit of these two items, which item is having highest profit? Obviously item 1. So that's why here we are at the current capacity 2. We are not considering the item 2. We are considering the item 1, since this profit is high. Clear? So next we are supposed to find out what is V of 2 comma 3. So again, the maximum of, you go to the previous row, same column entry, that is 12, comma, what is the value of this item? 10 plus, you go to the previous row and WI column towards left. So one column towards left. What is the entry here is 12. So if you add 10 plus 12 is 22. Whichever is maximum, 22. So that's why V of 2 comma 3 is 22. You look at here. Okay. So what is the current capacity we are looking? 3. The current capacity of the sack is 3. Okay. Whatever the items so far you are considering, this 1 and 2. Okay. If you add these weight together, 2 plus 1 is obviously 3, which means that both the items can fit into the sack. If so, obviously the profit of the two item has to be added. No. So that's why 12 plus 10 is 22. Logically, you can also think of that. But actually, we are getting this value by substituting the values in the recurrence. Okay. So you may ask that why we are storing these values. Every time the sub problem you may need, that is V of 1 comma 2, sometimes you need when you are solving this another instance for also. So instead of recomputing the value, directly we are looking to the table and we are getting what is the value of V of 1 comma 2. That is the advantage of DP. Okay, so you can easily know that how we have obtained the value V of 2 comma 3 as 22. Okay, so next we will compute what is the value of V of 2 comma 4. So again, what is the entry in its previous row, same column? 12. Okay, then what is the value of this item? 10, and you find out what is its one column towards left entry is 12. So 10 plus 12 is 22, whichever is maximum, 22. Again, which means that for the current capacity 4, both the items can fit. No, obviously for V of 2 comma 4 and as well as 2 comma 5, the value or the profit of the sack you can achieve at the moment. If you are considering these two items, you can achieve the maximum profit is 22. So next we have to go for this 3. Okay, so this is obviously 0 initially. Okay, so v of 3 comma 1. Okay, so you can find out the previous entry value was 10. Previous entry value was 10. Again you have to, what is the value of this item? 20. And what is that wi 3? Okay, so there are no entries in its 3 columns towards left. Okay, so obviously this is going to be the profit of this. So which means that what indicates what is the current capacity we are looking? 1. What is the weight of this item? 3. So which cannot be fit into the sack at all. So that's why for this column v of 3 comma 1 and v of 3 comma 2, okay, whatever the previous profit item, that is v of I minus 1 comma j, that is going to be replaced. Okay, when you come to here v of 3 comma 3, okay, so you have to find out whether you have to consider the previous one or this one. Okay, so what is the entry? I'll write it, v of 3 comma 3. So the entry in the previous row, same column is 22, comma, what is the value of this item? 20 plus, and you add the entry in the previous row wi column towards left. Okay, so 1 2 3, the entry is 0. So whichever is maximum, 22. Okay, so which means that for the current capacity 3, okay, so if you add the previous profit is 22. Okay, so we cannot add this, okay, at the current capacity. If you are considering the third item alone, what is its profit? 20. Okay, but if you are considering the previous two items for the current capacity 3, what the profit we are achieving? 22. So obviously we have to maximize the profit, no? So that's why we are not considering this case item 3 for the capacity 3. Next we have to compute what is v of 3 comma 4. V of 3 comma 4 is equal to maximum of, what is the entry in the previous row, same column? 22, comma, what is the value of this item? 20 plus the same row, the entry in the wi column towards left. So 3, so 1 2 3, the value is 10. So whichever is maximum, 30. So that's why v of 3 comma 4 is 30. Okay, so you look at this, what is the current capacity is 4. Okay, if you are considering the previous two items, okay, if you are 3 means what is the profit we are achieving? If you are considering the previous two items at the moment, if you are considering those items, you are achieving the profit as 22. Instead of that, if you are considering this item alone for this current capacity 4, if you are considering the item 3 and item 2, 3 plus 1 is 4. So you will got it as 20 plus 1, 30 is, sorry, 20 plus 10 is 30. That's why. Okay, so again this column v of 3 comma 5 is the value in the previous row, same column is 22, and you add the value along with this wi column towards left. So 1 2 3, so 20 plus 2 is 32, whichever is maximum, 32. So which means that at the current capacity 5, you can consider this item 3 along with w1. So 2 plus 3 is 5, no? So that's why 12 plus 20 is 32. So likewise you fill up this table also by applying the same concept. Okay, so what we have achieved is v of 4 comma 5 is 37. So this is what the maximum profit, if you are considering all these 4 items, the subset of this item, at the maximum profit what you can achieve here is only the 37. So by with the help of that recurrence, we have solved the solution to the sub problems. Okay, that is when you are considering the first item at various capacity, or considering the second item, or these two together at the various capacity of those sack, what is the profit you are achieving. Okay, then we are supposed to find out what is the solution to our main problem. So the solution is, the optimal solution is V of 4 comma 5, that is 37. Okay, so the thing is, when you are considering that item, we have to go from bottom up. Okay, so V of I, when you are considering this item V of I into the sack, you have to consider the profit of that with V of I minus 1 for the same capacity. If both are equal, then you are not supposed to consider V of I. So that is V of I should not be equal to V of I minus 1 comma j. Sorry, that is at the level capacity. V of I comma j should not be equivalent to V of I minus 1 comma j. That is what I am saying is, to find out the optimal solution, you look at this value when you are considering that item V of I comma j. So j means, keep it in your mind, that is at the current capacity of the sack. When you are considering that item, the profit of that item should not equivalent to the profit of the previous item at the same capacity. Then only you are including this V of that item. Okay, so V of 4 comma 5 is 37. Then you have to consider that V of 4 comma 5 with V of 3 comma 5. That is, you have to backtrack the table. Okay, from the last item to this. So the item 4 has to be included in the sack. Since V of 4 comma 5 is greater than V of 3 comma 5, that is 35 is greater than 32. You can look at the table. Okay. So that's why the fourth item can be filled into the sack. So when you are considering the fourth item into the sack, okay, the current capacity what we are looking is 5. So the weight of this fourth item is 2. Okay. So 5 minus 2 is equal to 3. So you have to consider the remaining items for the capacity 3, not for capacity 5. Okay. So for V of the previous item is 3, no. So you have to consider V of 3 comma 3. Once again I'll repeat. Since V of 4 comma 5 is greater than V of 3 comma 5, so fourth item is included in the sack. If you are put that item into the sack, which leaves the current capacity of the sack is 5 minus 2 equal to 3. So you have to consider the remaining items for the capacity is only 3. So V of 3 comma 3. Okay. So again, since V of 3 comma 3 is equivalent to V of 2 comma 3, the item 3 need not be in an optimal subset. Okay. Both the value will have same. So the item 3 cannot be considered. Okay. So next you have to check whether second item can be included in the sack. So since V of 2 comma 3 is greater than V of 1 comma 3, so item 2 is part of an optimal selection. Okay. Which leaves V of 1 comma 3 minus 1, because the second item weight is 1, 3 minus 1 is 2. Okay. So the item 2 was included, item 4 is included, which leaves the current capacity of the sack is 2. So you have to look at this whether V of 1 comma 2 is greater than V of 0 comma 2. Obviously it is true. Okay. Because there are no item 0, no. So the item 1 is included in the solution. Okay, so which leaves the current capacity of the sack as 0, which means that the sack is filled. So the optimal solution is the item 1 and item 2 and item 4 is filled into the sack with the maximum profit as 37. So the advantage of this DP is the subproblems are solved only once. The results of the subproblems are recorded in the table. Whenever you need that solution, you look into the table and get what is that value. Okay. In order to find this optimal solution from the table, you have to backtrack to this. So when the item is considered into the sack, means you have to ensure that V of I comma j should not be equivalent to V of I minus 1 comma j. So which means that when you are considering that item, the profit of the item should be greater than the previous profit item. Then only you can consider into that item. So this is your final optimal solution for the instance what they have discussed. Okay. Hope you understand what is the concept of dynamic programming and how to solve knapsack problem with help of this DP concept. Thank you.